goodness. There we go. Now we're cooking with fire. Okay. All right. Let's get started. We only have 2 lectures left and then an exam review, so we're going to get right into it. 6.3 to 6.5 is being graded. The solutions are available. 6.6 is due today. You have 6.7 due Friday, 6.7 due Monday, 6.8 due Wednesday, and then that's it. That's it for the homework to answer your question. That's how many we have. The bonus homework, however, that's still open, so that's free homework points. Okay, so today what we're going to do is we're going to do an example with a high CB value. And I told you before that there were differences between discretely braced beam design with low CB values and ones with high CB values. But one, I didn't explain what that even meant, and two, I didn't define how it would affect things. Like, what does it mean to be a high CB value, and how does it change the design? And so hopefully after what we do today, you'll kind of get the idea. Now, let's go through discretely braced beam design and make sure we understand the process. Okay, so first off, we compute the factored moment and the factored shear using an assumed self-weight, or if it's given, make sure that we're accounting for it. Again, the shear typically doesn't affect the design at the end of the day, but if we're doing the structural analysis, we might as well do it all. Next, we compute the moment of inertia based on deflection limit. So we compute what is the required IX value for whatever beam we pick. Okay, we determine our CB value and our LB value for design. If possible, I'd like to use table 3.1. You know that if you have an odd loading scenario, let's just say, and table 3.1 isn't going to work, that you could just do some structural analysis and compute CB yourself. We had a homework dedicated just to that, but hopefully we can use table 3.1. Then what we do is we go to table 3.10 for our design. On the x-axis, we go in with our unbraced length. On the y-axis, we go in with MU over CB for your design and pick a shape. Once you have that shape, you verify that the moment of inertia is good enough. If not, ignore all this and go to table 3.3 and then analyze the section for shear moment and deflection. And once that's good, you're done. Now, I want to make sure you all pay attention to this. This is kind of important. And then the next slide is very important. So what if you have a beam like this where you have different unbraced segments, different CB values, different MUs? So how do you go about it? So what you do for this problem is each segment could have a different performance. Each segment could have a different performance ratio. So typically what I do is I would just pick the segment with the largest MU over CB or the largest LB. There's a good chance that they are the same segment. If not, go with the one that has the largest moment. Goodness gracious. I don't know anybody from that city in Georgia. That is probably a spam call. Okay. So once you pick a segment for design and you have a trial shape, you need to analyze all the segments to verify the capacity. Again, it's possible that even the segment that has the largest bending moment might not be the one that governs because of the effects of CB and LB, etc. Some may be possibly neglected. So for instance, if you look at a beam like this and there's 3 segments, and let's say we're looking at this 3rd segment, and it has the shortest LB, the highest CB, and the lowest moment, it's not going to govern, so you don't even need to look at it. But when in doubt, just look at them all. Okay, does that make sense? Okay, I figured it would. That's just sort of a formality. This is what I want to talk about today: high CB values. And I want to conduct a quick exercise to explain high CB values. And the easiest way to explain it is to go through an exercise. So I want everybody to break out your AISC 15th edition steel construction manual. I want you to break out table 310 because I need your help on this one. All right, so help me out. I want to do a design real quick. I want to design a beam for this data. So let's take a look at it. So we have a beam that requires a factored moment resistance of 1020 foot kips. We have a moment of inertia requirement of 2,800 inches to the fourth. Bless you. Now look at our CB value. Look at that value, a CB of 2. That's pretty high. That's a pretty large value. I still haven't rigorously defined what I mean by high CB values, but that'll become clear after this. Now we have an LB value of 20 feet. Now do I go into table 310 with 1020? No. What I do is I go into table 310 with this. I go in with an LB of 20 feet, but the MU value we go in with is our moment, but we divide out our CB value. So we get a CB, an MU over CB of 510. So what section are you finding? W24 by 84. Say it again, W24 by 84? Survey says, well, by golly gosh gee, that's what I found too. That's crazy. It's like we're all on the same page or something. Now, I need your help on something else. What is that shape's phi MP? 840. Okay. All right. For a W24 by 84, phi MP is 840. Anybody notice a problem with this? Yeah, see that's the money right there. Here's our capacity. Here's our moment. What did I tell you from day one about flexural capacity? I don't care what the equations say for the capacity. The capacity is limited to MP every time, right? And here our phi MP is less than the factored moment. This is a false positive, okay? This is a case where table 310 told us that that's the answer, but it's not, okay? It's not because of the following, just to make sure this is clear. So here's the problem. The maximum MU is 1020 foot kips, but the maximum possible phi MN is phi MP, which is 840, okay? This section doesn't work, all right? If you remember the way that this, oh, I need to put on my pen here. If you remember the way the LTB curve works is we have this, sort of shaped curve, right? And then we have the effect of what happens when you employ CB. What I'm saying is that when you have high CB values, you are predicting a capacity that's like all the way up here. But in actuality, the capacity is limited to MP. So you're looking up a section that looks good, and it's not, okay? So it leads to a false positive. Again, the CB value serves to increase the flexural moment capacity, but it can't increase it past phi MM. And to be clear, our differential equation solution, remember how we treated moment as a constant, and so that corresponded to a CB of 1? Well, that differential equation solution assumes that you have to reach that capacity everywhere on the beam, but that's not really fair. If you have a beam, a simply supported beam with a point load right in the middle, you only need to develop that maximum flexural capacity at the middle. So that's what CB tends to do. It tends to augment the capacity based on the fact that you don't need to develop that maximum capacity everywhere, just at your key locations. But you can't go past MP. So because you can't account for this cutoff, this sort of cutoff in capacity during the usage of table 310, you're getting a section that looks good, and it really isn't, okay? This is one of the big reasons why you really have to analyze the section once you nail one down. Now, does everybody understand the problem? Okay, now there's the problem. What do we do about it? Okay, so here's the problem, right? And this is what we all looked up, right? We got the 20, 510, and you looked up that section, right? So you found a section that doesn't work. What do you do when you get a false positive? Just look at the next one. Just keep looking at the next one, keep looking at the next one, and keep trying to go this way and find one that works, okay? Keep going until you find a section that's going to be viable. And again, it might be easier to trace upwards as opposed to this way, but let me show you how that works, okay? So this is sort of the way that I might suggest that you do it. So I'm going to suggest maybe that you set up a table. So follow along with me, okay? So we have here our trial section, and we set a W24 by 84. We found that from table 310, okay? Now, we have a factored moment of 1,020 foot kips, and our PMP is 840, right? And we got that from table 3.2, right? Now, keep in mind, we do have a moment of inertia requirement of 2,800 inches to the fourth, and so you might ask, well, what's the moment of inertia of this shape? Who cares what the moment of inertia of that shape is, because it doesn't work, right? But I just want you to keep in mind that this is something that we have to look at as well. So we go to the next section. The next section is a W27 by 84, okay? Now, its factored moment is still 1020 foot kips. What's the PMP for a W27 by 84? With your AISC 15th edition steel construction manuals in table 3.2. 915, right? So here's 915. It's still no good, right? Now, again, we have a moment of inertia requirement of 2,800 inches to the fourth. Again, who cares? So what's the next section? Well, the next section that shows up in the spec is a W30 by 90, okay? Again, based on a factored moment of 1020 foot kips, what's its capacity? Okay, that one might be a viable pick, right? But if we're going to do this, let's go ahead and check our moment of inertia. What's the moment of inertia? Well, you know, we still have to analyze it. What's our moment of inertia for a W30 by 90? Okay, so now, okay, we got some stuff here. We got some value here. We've got a section. We don't know whether or not it does work. We still need to do the math and check it. But it's at least viable from a flexural capacity standpoint and a moment of inertia standpoint, okay? Now, I would argue that if you get to this point right here and the moment of inertia still isn't big enough, abandon all this and just find a section based out of table 3.3, okay? Because it's telling you that your shape is not governed by strength, it's governed by deflection, okay? Does that make sense? Okay. Let's do a problem. Now, I picked a problem where the CB value is high, okay? So let's design a discretely braced beam for this problem. Now, look right here. Look at this note here on the bottom. I say be prepared. There's going to be a lot of flipping back and forth on this problem, so just be aware of it, okay? So we're going to design this beam to ensure a live load deflection limit of L over 360, and we're going to be doing a lot of page slipping. The only dead load is the self-weight of the beam, which we're assuming to be 100 pounds per foot. And the live load, we got 65 kips right in the middle of this beam. So this beam's got a lot of load in the middle. So let's see what happens. All right, bear with me. So again, you're going to be doing a lot of page flipping between table 310 and table 3.2. So just be aware of that's going to happen. Okay. Okay. All right. So the first thing that we're going to do for this problem is we're going to treat it very much like a lot of the problems that we've done in the past, right? We have a simply supported beam, point load in the middle. We were given our LBs and our CBs. I went ahead and gave you the CB value for the purposes of this problem. We've got two segments on the beam, but really I only need to consider one of them because they're both the same. They both have the same CB, they both have the same LB, and they're both going to have the same maximum moment. So let's do a little bit of figuring here, okay? So step one, compute MU and VU. So W naught is 100 pounds per foot or 0.1 kips per foot. And L is, what is L? How long is the beam? 20 feet. It's not 10 feet. Don't confuse L with LB. So our dead load moment is just that. Here I said 10. When I told you don't confuse them, and I went and just wrote it. And nobody stopped me. So that does not go on the tally mark because I caught it before you did.
That's why we didn't stop you, so it would be a tally mark.
That doesn't follow. Again, I control the rules. It's pretty, you know, I know it's pretty corrupt. So 20 times 20 is 400 times 0.1 is 40 over 8 is 5. That's 5 foot kips. And then VD is WL over 2. So 20 over 2 is 10, is 1 kip. All right. Now we've been given a live load of 65 kips and a length of 20 feet, right? So that means we turn that into a distributed load, right? Is that right? Thank you. No, we don't do that. And if you do that, that is the Dr. Mike hand slapping technique. Don't do it. No. We say that our live load moment is what? PL over 4. So 65 kips times 20 feet over 4, which is 65 times 5. 65 times 5 is 325. And VL is what? PL something. PL over 2. So So 1.2 times the dead plus 1.6 times the live. That one I think I can do for you. That's 526. I'm going through this part kind of quickly because I think it's kind of repetitive from the stuff that we've done before. And this is 53.2. Let me stop for a sec. Again, I went through this pretty quickly because I think we've had like 3 or 4 problems where it's like the same thing over and over again, you know. So I didn't want to waste time focusing on the stuff that I'm pretty sure we're all pretty comfortable with. Now, I also think that we're all pretty comfortable with this part, compute required IX. So what we do is we take our live load deflection limit, which our live load deflection limit is L over 360 for this problem, right? Don't forget to do that. All right, and what do we get here? I think we can, yeah, I think we can go through that, 0.67. Now, what is the maximum deflection formula? Because it's not 5WL to the 4th over 384 EI, because that would involve the Dr. Mike hand slapping technique by turning our point load into a distributed load. No. Boom! PL cubed over 48 EI. And y'all know that if you were, you know, on a desert island and didn't have your AISC 15th edition steel construction manual, you could always just use the method of virtual work, integral little m big M over EI. Yeah, that is a fair point.
What if you have to build your structure?
Yeah, your survival shelter.
Steel. Yeah, for some reason I just have steel.
So, I think the biology department would have a couple words about that. Okay, so what we're going to do is we're going to take this equation, solve for Ix, and so all I'm doing is flipping these two, and I'll plug this value in to figure out what my moment of inertia needs to be. So, I've got 65 kips, I've got 20 feet to the third, 48, 29,000 KSI, this is 0.67 inches. Am I missing something? There you go. And so what's my IX min going to be? 963 point, or wait, say it again? 968.3? Did I get that right?
I got 963.5.
Oh, maybe I have a typo. I will cede to the class on this one. That's also not a reason for a tally mark because I'm agreeing with you.
You're fighting off me like every time. Students note clip when it's
I'm close to 7, but I'm not quite there. Not quite there. Okay.
If you did 0.666666 repeating, you get the.
Oh, so I was right? Is that what we're... Oh, okay. Oh,
968.3.
so I was right initially? Oh, okay. Just, yeah, I'll just remember that.
So you were wrong by agreeing.
I guess. So we'll do it like this. So there's like, you know how there's like a real number line and an imaginary number line? We'll say this is like an imaginary tally mark. We'll do that. Okay. So let's select a trial shape. Now, this is going to require a lot of back and forth, so just bear with me, okay? Now, we were given, and so let's keep in mind what we're doing. LB is 10 feet. MU is 526. And then CB is 1.67. So we're going to go into the table with 10 feet and MU over CB of what? Well, I know, but no, MU over CB. I mean.
314.9. So I guess
Yeah, that for purposes of looking it up in the table, that's probably close enough. So we'll say 315. Now, everybody watch what I'm doing, okay? Because we're going to track this together, okay? So we're going to have trial, okay? We're going to have phi MP, and then we're going to have IX. Remember, IX min is 963.5 or 968.3, close enough. Okay. So help me out. We're going to do a lot of page flipping on this, so just be aware of it. Okay? So give me the first trial shape that you find that has an LB of 10 feet and an MU of 315. What's the first trial shape? Okay, a W21 by 48. I want to make sure everybody is finding that. Is everybody finding that?
I asked a question.
You most certainly can.
why in the top left does it say that this is CB equals 1? When we divide the MU by CB, does that make it CB equal 1, I guess?
Yes.
Okay, that's
But again, false positives can happen as a result, which is what we're doing here.
Okay.
All right? Now, so is everybody finding the W21 by 48? Now, for the W21 by 48, what's phi and P? 398. What does that mean? It's no good, because remember, that is our applied moment. That's our actual applied moment. So what we're going to do is we're going to go back to table 310, and we're going to find the W21 by 48 and go up to the next one. What's the next one? The W18 by 55. And what's its phi and P? 420. Is that good? No. Because again, it's got to be over 526. Okay? So we go back to table 310. What's the next shape? 21 by 55. Is everybody seeing that? I don't want to go too fast. Is everybody seeing that? Okay. What's its phi and P? 473. Still not good. By golly, gosh, gee. All right, what about the next one? Say it again. W18 by 60. What's its phi and P?
Nah, that one's not a solid line. It gets solid at the bottom, but when it goes up top, it turns powder.
Well, I mean, it could be a viable candidate, though. What's its phi and P? 461. So it doesn't matter anyways. Man, talk about iteration. What about the next one?
21 by 62.
21 by 62. Now, what's its phi and P?
540.
Ooh, 540. That means that might be a viable choice. Oh, no. All right. What's its moment of inertia? Say it again. Now, is that bigger than 963.5? Is that bigger than 968.3? The decimals matter. That was mean. I'm sorry. I got trolled by actress jokes. They put me in a mood. What can I say? All right. So now I would say we have a shape that we can actually feasibly analyze. So we're in step 5. Now, I guess what I should mention is that this is also kind of step 4 right here, because what we're doing is checking the moment of inertia for our given trial shape. So now we'll analyze the W21 by 62. Now, when I look at W21 by 62, the first thing I clue into is that number 62. What does that number tell me? The weight per foot, but what does that tell me? It's lighter than what we assumed. We assumed that the beam weighed 100 pounds per foot. So 62 pounds per foot is less than the assumption. So we don't need to update MU and VU. We can just use them from before. And if they work, if it works for that, it is certainly going to work for that weight. So let's do some analyzing. What's LP and LR? 6.25 and 18.1. Now, this is zone what? 2, because LB is 10 feet. All right? So in order to do a zone 2 analysis, we need a couple of things. We need our CB value. Oh, we need our CB value, which is 1.67. We need our phi and P, which we already looked that up. That was 540. And we need our phi BF. What's phi BF? 17.5. So we compute our zone 2 formula. And again, all this is just linear interpolation. Like it's y minus y1 equals m times x minus x1, because phi BF, that's the slope of the line. So this is 1.67 times 540 minus 17.5 kips times 10 feet minus 6.25 feet. What does that come out to be? 792.2. And remember, phi mn is the minimum of CB times all that hullabaloo that we just computed, or phi MP. And so what is that going to be? What's the minimum of this and phi MP? It's just phi MP. Now that should make sense for this problem. Remember all that iteration that we had to do? Think about the iteration that we had to do. We had to do all this iteration because what we were trying to do is find a section that wasn't a false positive. And why were they false positive? Because the capacity was cut off at MP, right? And then we do the math for this section and we find that the capacity is MP. So that shouldn't be that big of a surprise, okay? Now, MU is, what was MU again? 526. Is this section okay from a flexural capacity standpoint? Yes. Now, if you want, you can compute a performance ratio, and it's pretty high. It ends up being like 0.974. That's pretty large. That's a pretty efficient design right there. 97% efficient. That's not bad. Now, for shear, VU is 53.2 kips. What is phi VN? 252. Is it good? Yeah, it's good. If you want its performance ratio, it's 0.211.
Pretty good.
Yeah, it's fine. It's fine. And then finally, if you want, you can do the deflections. You get that the deflection limit is, again, 0.667 inches, and the actual deflection is PL cubed over 48 EI. Only now we're using the actual I of 1330, and when you chug that out, you get a value of 0.485 inches. So again, that's okay. And if you want a performance ratio for the deflection, it ends up being something like 0.728. Again, I'm going through these calculations pretty quickly. because this stuff I think we're pretty familiar with. You know, we've done quite a few of those. Okay. Let me stop for a sec, let everybody soak this in, because there's one final question I want to answer, and you'll see what that is here in a second. But before we move on, any questions? Okay. Is there anything here in this calculation that I haven't shown you how to do yet? I haven't shown you how to compute? The shear capacity. Maybe we ought to talk about that. Let's talk about the shear capacity. It's like I was ready for it or something. This is a brief coverage of shear. Brief. Okay? So remember, Chapter D is on tension members. Chapter E is on compression. Chapter F is on bending. Chapter G is shear. So let's talk a little bit about it. Let's go back to Engineering 216 land. So in Engineering 216, Mechanics of Deformable Bodies, everybody's favorite class, you spend a lot of time in that class learning the big four stress formulas here: axial stress, torsion, bending, and shear. Now, bending, sigma equals my over I. That doesn't change dependent upon the type of cross-section that you look at, but shear does, okay? What you find is that our expression VQ over IB is the means of determining transverse shear stresses across the section, okay? Now, if you want a very simple explanation for what's going on, here's what's going on, okay? Now, imagine that this book is a beam, okay? I take the beam and I bend it. It doesn't have much flexural stiffness, like it just goes, right? But if I were to take some glue and a lot of time and literally glue every single one of these pages together and press them together and glue them, and then do this, this would be a lot tougher. And the reason why is because between the pages freely slide along one another, right? Okay? Gluing them together would ensure that the transverse shear between the pages was restrained. That's what this is, right? That's what's going on in the shear diagram. That's what the shear studs connecting the concrete deck to the steel beam are doing. They are providing that transverse shear resistance. Now, the formula for computing that is VQ over IB, and what's really interesting about this formula is the denominator, B. B is the width of the beam. When you're looking at I-beams, what you have is you have a width, bam. You have a sudden change in width. And the width suddenly gets smaller. So if the width suddenly gets smaller, the stress suddenly jumps up. And what you find in I-beams is there's a boatload of stress right there in the web. So what do we do as engineers? Typically, when we design, we only focus on the web in shear. So I'm going to pull this video up over here. Let's see, 2CY W ZRR LF7W LF7U. Okay, this is perfect. All right. Okay. Here's what happens in a plate girder, okay? So here's a beam, right? And what we're looking at is the web of the beam, right? So this is the bottom flange down here. This is the top flange up here. And here is the web, okay? Now we are taking this and we are putting it through a shear test, right? So there's a reaction here pushing up, and there's a load here pushing down. So this panel is under a very high shear load, okay? Now what Moore's circle tells us is that if you have an element under pure shear and you rotate it 45 degrees, what you have is tension one way, compression another. I seem to remember that things in compression like to buckle. So as we load this, what happens is, boom, we start to get a shear buckle, okay? That shear buckle occurs at around a 45-degree angle because that's what's going on in terms of our principal stresses. Does everybody kind of see this? It's the same reason why in concrete design, let me pause that. See, it's the same reason in concrete design, if you did the same thing, you would find a crack, and you would find a crack going this way, the other way. The reason why is concrete is a material that is very weak in tension, but strong in compression. So instead of failing this way, it fails this way. It opens that way. So you get a crack under tension. That's why inside concrete beams, you put stirrups to withstand the resulting shear. In steel land, what we do is we utilize stiffeners. So if you're ever driving down the road and you see these plates going up and down on a plate girder, that's what they're for. Okay, they really sort of serve two purposes. One is to resist, or is to increase the section's capacity against shear, and the second is to serve as a means for connecting cross frames or diaphragms or what have you. But those are the two real big purposes. Now, what we find in buildings is that you hardly never need these, okay? Because look at what we've been doing. Look at the problems we've been looking at. We've had performance ratios of 0.2 for shear. It hasn't been a big deal. So we really haven't talked about it. But in bridge land, it becomes a much bigger thing to consider. Now, when you look at the capacity for webs in shear according to Chapter G, what we find is this. Okay, so let's look at the spec a little bit. What it says is that in general, our phi value is 0.9, but there are a lot of cases where phi is 1, and in fact, phi is 1 for most W sections with a yield stress of 50 KSI. In fact, if you look at this user's note, there's only a few cases where it's 0.9. Everything else, it's 1. So it says right here, all current ASTM shapes except these have a phi value of 1. So these would have a phi value of 0.9. Everything else has a value of 1. And the way that we determine which one of these has a phi value of 0.9 is we look at the slenderness of the web, the ratio of how tall the web is to how thick it is. And so the webs that are inherently thin, we use a phi value of 0.9, whereas the others we use a phi value of 1. That's the phi value. In terms of the capacity, there's a lot of hullabaloo here about computing a web buckling coefficient, but that never happens with rolled W shapes because the webs for rolled W shapes are so beefy that buckling never really ends up being a problem. So we end up having this equation times CV1, but CV1, that buckling coefficient, is always equal to 1 for all rolled W shapes that are 50 KSI. But the capacity is computed by taking Fy times the area of the web, so depth times the thickness, times this value of 0.6. There's that dastardly 0.6 that shows up again. It's almost like things in shear fail under a lower stress due to that whole von Mises yield criterion we talked about in exam 1. See, it all shows up again, okay? So to give you kind of an idea of how this works, let's do a real quick example of looking at a W24 by 62, and I think you'll find this is really simple. All right, let's see. Hold on. All right. So what we do for a W24 by 62 is we need to look up some properties. So what the? Is it not liking me? All right, well, we'll go to the notebook. That's why I have it. So, can somebody tell me what is the D value and the TW value for a W24 by 62? Say it again. Not exactly. Not exactly. Say it again. And TW. .43. So if we wanted, we can compute 0.6 Fy AW. So that's going to be 0.6 times 50 KSI times 23.7 inches times 0.430. What is that? $305.73. Maybe that rounds to, I don't know, 306. By golly gosh, gee. See, what happens is, see, phi VN is computed by taking phi times this times this buckling constant, okay? Now, what I can tell you is that the buckling constant doesn't end up being a problem for rolled W shapes that are 50 KSI. You can look at the math and see, but this value is always going to be 1 for rolled W shapes 50 KSI. So equals 1 for 50 KSI W shapes. And this equals 1 for most W shapes. Okay? And if you want some detail on what I mean by most, well, it's right here. Well, we're going to talk about this a little bit more in detail on Monday. But basically, anytime that your web is less than or equal to 2.24 square root of E over Fy, then phi is 1. And there's only a few shapes where phi is not 1, and the W24 by 62 isn't listed. And so I think math tells me that if you take a number and keep multiplying it by 1, you get the same number. So phi VN is 306 kips, which is exactly what the table listed. I can tell you that the vast majority of phi VN values in the table are just 0.6 times Fy times the area of the web. There's only a few of them where phi is 0.9. And you can very easily identify those, but we'll get into that discussion a little bit more in detail on Monday. You all have a wonderful weekend. I will see you then.
Never forgot